Okay, let's talk about electrochemical cells, and then we'll work up to batteries. Okay. So it was found that way back when, that if you were to say take two different types of metal, say for instance copper and zinc, and you were to wet a piece of fabric, okay, like so, with an acidic compound, and you were to just lay one on top of the other, and you could actually keep stacking these guys on up, all right, layer after layer, that you could actually create, if you hooked wires from the top to the bottom of this thing, basically a potential difference, and you can make electric pixies run through a wire and do some work for you. Okay? So if we were to attach a wire here, you know, we might be able to detect that there's a voltage there, and we might, if we do this enough, we stack it high enough, we might actually be able to run something useful with this. Okay. So you don't need anything really other than two disparate types of metal and a salt bridge, if you want, or just you know, something that allows ion transfer between these guys here, right? So how this was looked at in another way, and this, by the way, is called a Voltaic pile, and was invented by Alessandro Volta. And interestingly, each one of these provides a set amount of voltage, and when you stack them up, those voltages add. So essentially what this is a very primitive battery, okay? Each zinc-copper pairing is considered to be a cell. Okay, and a bunch of cells is a battery of cells, just like a battery of guns would be, you know, multiple guns all lined up. So that's where the term battery comes from. So without going too far into the chemistry, basically you have what's called a redox reaction going on here. The electrolytic material in here could be, say, something like some sort of metal sulfate. The ions will be attracted either one way or the other. Now this one, conventional current-wise, flows from zinc toward copper. So with conventional current, you would consider this to be positive and this to be negative, and you would get the positive pixies flowing that way. Now, tell a chemist that, they'll get very upset, because in real life, what's really going on is electrons are flowing the other way. Okay, but let's not believe that point. All we really need to understand here is that certain metals have a stronger attraction or affinity for charge than others do. And if you set them up in the correct way, you can actually make a PD. So kind of a more common way that you might see this in chemistry, you might see something like this. Okay, you might have a zinc bar, and you might put some zinc sulfate in here, ZnS4, and then you might have sort of what's called a salt bridge, which could be as simple really as a twisted electrolyte soaked paper towel will work. Yeah, and then you have another, you know, chamber over here. You're going to put the copper in here. You might have something like copper sulfate. It doesn't really matter so much what this is. It does not necessarily have to be acidic, although you could just use a generic acid, which will then dissolve the metal into itself. You know, so if you put a little hydrochloric acid in here, you'd end up with some zinc chloride in here and some copper sulfate in there. And then what you can do is you could put a wire connecting these two together, and you could put some sort of whatever it is you're looking to make chooch in there. So, you know, a light bulb, or you can put a heater or whatever it is, and then you can test the voltage across here. I wish shooch was my word, but it sure is not. This guy. Watch his videos, they're great, but they're swearing, so heads up. Okay, anyway. Okay, so in this case, we will have conventional current flowing here to here. Okay? All right, so again, without over chemistrying it, do you know this little saying? This old saying, Leo goes grr. So, let's just make sure we say this right. Yeah. Sorry, guys. I actually drew this. This is electron flow here, right? So, what happens here is zinc. Zinc is the more active metal here. It is capable of pushing its electrons over onto copper. Okay. Right. So exactly. Yeah. Yeah. Copper is reduced, and zinc is zinc is reducing copper. So zinc is being oxidized, but it's reducing copper. So zinc is a reducing agent. Correct. That's right. That's right. So conventional flow is actually this way, right? This is how an engineer would view it. My bad on that. My mistake on that. Okay, electron flow goes this way, but the engineers and the electrical guys, the electricians, and so on, view it as positive charge moving this way. Okay, in reality, unless you're dealing with semiconductors, you don't have to pay too much attention to which way the flow is actually happening here. But in chemistry, you definitely do. So what goes on here is essentially this, right? So zinc, positive zinc ions then enter this solution, right? Zn, and I believe they're 2 plus. I'm not exactly sure. Not exactly sure if that matters either. Yeah, they are 2 plus. And then out of the salt bridge, right? Since you're getting more and more positive, what will happen is electrons will leave the salt bridge, right? It acts as a supply of electrons to balance out the new zincs that are coming into here, right? And then electrons come over here. Well, if you have copper sulfate, what that means is you have positive copper ions here that come on and start to actually plate out onto this this piece of metal here, right? And they become reduced. The copper in here gets reduced, okay? So electrons flow this way, conventional current flows that way, and that's how a battery works, basically. Exactly, you're plating copper onto itself, and well, it's copper metal, right? So copper 2 plus gets reduced to copper metal, right? It becomes less positive. Um, yes, and the zinc wastes away, right? It rots away with time. So the zinc plate will actually wear out because you're losing zinc into solution. It'll actually, you could say it, yeah, it dissolves away into the solution here. And that's the essentially basics behind how a battery works. So what we're interested with in this scenario here is we are interested in EMF here. So EMF is the electron motive force. In other words, how much pressure is there on these electrons pushing from one side to another? And do you guys have any idea how many electrons would push across here? Or sorry, I should say, that was a terrible question. Do you have any idea how we would measure the electron motive force? What units would we use for that? Well, actually just volts. You could, electron volts are something else, right? They're a unit of energy. We just want to know in terms of joules per coulomb how much pushing is going on behind these electrons. Okay, so in this scenario right here, you will get about 1.1 volts. Okay, roughly 1.1 volts. If you start stacking, like we mentioned before, you get 1.1 volts per stack, right? So if we have, you know, your zinc, and your copper, well, you're going to get 2.2 volts from this scenario, and so on, and you can keep adding them on up, okay? So the symbol for a single cell is just this, okay? With the big plate being positive and the small plate being negative. So in this case, we're going to have zinc here and copper here, okay? A battery is just drawn as a series of these things. So if we did zinc, copper, zinc, copper, zinc, copper, we would get a 3.3 volt battery, like so. Make sense? So there we go. Now, the last thing we need to consider is that in order for flow to happen inside a battery, we have to consider that there is resistance here, all right? There's a resistance internally within the battery because essentially like physical objects have to move, right? Ions of matter have to move from one place to another. And we also know that there's resistance even within the wires themselves. So batteries have what is called an internal resistance. So if we look at a battery like this, we would say this: E, the electron motive force measured in volts. So this is EMF in volts, is found as this. Okay, so let's say we put this into a circuit with some big resistor, okay? And we have some EMF in the battery, but this battery also behaves as a small resistor itself, so a little r. So we look at the whole circuit and we understand that the current flow through the entire circuit is the same. So it's the same through the battery from one end to the other as it is through this big resistor. So what we end up with is this: IR, the current through the whole system, plus the current through the battery and its little resistance. So this is called the internal resistance of the battery. Little r equals internal resistance. Okay, and you can shorten this to just this. Since these are the same I's, you get this little formula here. Okay, so you can use that to sort some things out. So little r is battery internal resistance, and this is the load of the circuit here, the big R. And I believe this is given to you in your data booklet. And the last thing we'll talk about is primary and secondary cells. There are two types of battery. And basically, this is your non-rechargeable. Yeah, so primary cells are non-rechargeable. So designed to be used once. And secondary are your rechargeable batteries. Secondaries are becoming much more common these days. Obviously, there's lots of reasons why that might be economical. It's nice to be able to reuse a battery, and environmental. Throwing out batteries is not good for the environment.